quite good. I like his.
Yeah, and we invite Dr. Gerart again in June.
Good. Brilliant man. Brilliant man. This,
Yeah.
I hope you get some experimental attraction to that approach. It is an approach that I don't recall seeing that. If you look in the deep literature, there's always something there somewhere. Everybody, no matter what topic you think of, somebody has a paper somewhere, which is something that surprised me about looking at the deep literature. So I remember the fermionic cube I came up with. I started saying, somebody's probably done that. Then I found out Glashow himself was the first one to do it, which really surprised me. I thought that was I had no idea that had that long of a history or goes back to somebody who's that important in the standard model. But always interesting what you can find if you dig really deep into the literature. And original papers. I just love original papers. They're never what you think they are. They become kind of like a sacred literature that everybody just assumes everything is perfect in the paper. And of course, that's never true. It's never true. Because every paper is just a human undertaking. We all have our little things. It's just that when you have that as a critical starting point, you tend to forget that some of the thinking went into it is actually more interesting than the result they come out with, because they had to look at the problem from all sorts of different angles. And you lose those angles. You lose that insight that the original authors had. Einstein, my gosh, the way he would look at things, he was just, you couldn't stop his mind from examining all these different angles, and the angles were so different from what other people were looking at. But just an amazing mind. So you get into his papers, and it's just so impressive, and such a different way of analyzing some of the problems. But it's fun to kind of get into the mind a little bit. I think we're at 1. Do you want to wait to see if more join?
Okay.
Good to see you.
Thank you.
People start joining in the last minute.
Okay.
Just wait for a couple more minutes and see if they have problem to join.
So you'll give the recording in progress meeting and recording warning ahead of time, right?
I will hit the record button, so it will record the chat history. Yeah. So usually when we do a live stream, we don't need the recording, but I need the chat history. That's why I record it.
Yeah.
That is good, because we used to meet in Cambridge Quantum's office, but right now people are from all over the world, and to meet at the Cambridge Quantum, we need to pay $15 for the parking. So that doesn't make any sense nowadays.
I had forgotten this meeting is 1 day after Valentine's Day, but I also forgot Valentine's Day. My wife and I both fortunately, forgot it until the 13th. And then one of our sons mentioned it. And we go, oh, ouch, we had completely forgotten it. I have no idea why. Usually we pay attention to it, but just sort of slipped up on us this year.
This event is a Valentine's Day gift for your family.
Oh, yeah.
Yeah, I'm sure you'll get a lot of good feedback.
I hate to admit it, but I spent a lot of Valentine's Day. I even warned my wife, said, I think we have to, because I was doing some last minute I had the slides, but I was doing last minute preparations on them. So I did a lot of work for that during the afternoon.
Yeah.
We also got in a celebration, and we'll get another one in this coming week, because since we both forgot it, we both had to catch up a little bit.
You will get a lot of good feedback afterwards. People will love your talk. I can guarantee.
I, well, like I say, I had fun with this talk, and one of the reasons the slides are so detailed is just to give people some reference. And I'm not just throwing things out randomly, but actually this is a result of looking at a lot of papers and looking at them very closely and saying, what are they really saying there? And sometimes what they're really saying is surprising, quite surprising. An example I'll get into, but most people don't realize that modern physics for the last 30 or 40 years has abandoned special relativity. They don't believe in it anymore. Anytime I get into the talk, but that's remarkable. And the way it happened, I even remember when it happened because I remember people first started doing lattice theory for quantum chromodynamics. So I remember the event. I remember the first few papers and said, wow, this is a really good calculation technique. But then it took over. And people started believing the model more than what was actually showing up in the evidence. And it's just such an unusual sequence, but things drift in a curious fashion. So you got this powerful tool and everybody uses it. So you think, wow, I guess I've got it. I guess that because the tool's so powerful, it must be the reality. And that's always a little tricky because you say, but what's the full set of experimental evidence? And the experimental evidence for good old Einstein special relativity is the most rock solid evidence anywhere in science. So, want to be a little careful about abandoning that too casually. So interesting how some of these things proceed. Kurt Jamungo has had a really nice little snippet at the end of one of his reviews where he just talked about how since 1980, it's a very specific date, not a single Nobel Prize has been awarded for anything that is truly innovative in the sense that the Standard Model was. Standard Model was amazing. Those were such marvelous times. I just loved reading science articles at the time because everybody would come out with a new database insight into the nature of particle physics. And it was just such a wonderful time to watch physics. But then after that, it changed so dramatically because it kind of wraps up and then everything just paused. So Kurt Jamungo's point was that ever since 1980, all Nobel Prizes in physics have been for elaboration. And not a single one has been for something truly new. So he did quite a bit of analysis on it. And I think he was surprised by the result. Okay, the topic today is one that I've just found deeply interesting, which is when you look at the role of information in physics. And of course, that's been a topic. People have been fascinated by information in physics for a long time. But the particular focus that I've had, and this partly is coming from computer science background, is what is a bit? What is the nature of information? And you have to be a little careful about that because the definition of information is a little more nebulous in the way it's used sometimes than it should be. And we do have to be a little careful about those implications. So the title of the talk is Fairy Dust, and by that I refer to what I call chaos bits. Chaos bits are ones that are just generated that are not actually part of the physics itself when the physics is stable and at rest. They only come into being when you poke at it. You do some kind of damage to the system. And a classic example, which I didn't cover in the presentation, is you look at an electron orbital, you say there's an electron poking around in there somewhere. In terms of physical evidence, the only way you can ever say there's an electron poking around in that orbital is if you put an incredible amount of energy into the orbital and destroy it. So you have to be careful in the difference between generating chaos and actually having chaos. And they turn out to be two different things in different contexts. They also have a direct relevance to things like the idea of the vacuum density problem. Why is the vacuum so dense? If it's generative, you don't have that problem. If you make it into something where chaos controls everything and chaos cancels chaos, then yeah, you have all sorts of problems with vacuum density. So fairy dust in physics, possible paths for trying to get a better handle on new physics theory that does not contradict what we have. Extremely important that we preserve the content of the theories we have. But we need to do something because it's been a long time now that we've got a stasis in physics theory. I will put a brag on this. Someone else pointed this out to me. I didn't even realize it at first. When this whole thing of the DeepSeek came out, someone else looked at it and said, Terry, isn't this the holographic interpretation of large language models that you mentioned? And I had no idea. I was going back, is it? Okay. It turns out that what DeepSeek did, or in the report they issued 2 months after the last time I talked to the DC quantum computing meetup, they had followed one of several pieces of advice, probably completely unrelated, although at the same time, it's 2 months later, so I don't know. I have no idea. One of the recommendations I have pretty explicitly is that, yeah, you can save a lot of money if you break it up and realize it's holographic and realize that you have pseudo-dimensionality, and then you have a separate issue of data processing. So if you put those two into two separate categories, you have the potential to save an enormous amount of processing time and processing energy. So that was one of my suggestions with a partial quote up here. The innovation they did was pretty much just that. They did it in a very smart way. They pre-trained it with some stable, diverse things, which creates the pseudo-dimensionality that they need. And then lo and behold, all of a sudden, the data and everything just kind of collapsed, and you had a huge reduction in the energy, with which they then, for at least for a few days, caused $1 trillion drop in stocks for some of their competitors with this. So I bring this out as a preface to this talk, but obviously it is a brag, because I honestly think DC Quantum Computing Meetup had a real impact with this one. That it made some difference by presenting a different way of modeling the same issue that people were looking at. I also use it as a brag of saying that sometimes we need to look at different ways, different mathematical models, different ways of approaching the same problem. And in this case, I think the holographic interpretation of large language models is a very good model for it. And also, it's not done yet. The one that they grabbed was the least radical of at least 3 suggestions that I made for this. So the idea of that, first of all, treating the bits as holographic medium produces profound differences in how you would organize these chips, right down to the silicon level. And the other impact, which also has not been explored as far as I know, is that optical holography, holographic storage, is a real thing. I mean, that's an existing technology. And I think there's an intriguing possibility that if you use optical Fourier transforms, which are so much cheaper than accidental matrix multiplication version of it, which I think is what we're doing, that you have a real impact for this. So this was kind of fun. It just like, oh, wow, yeah, that may have had an impact. And even if it didn't, it was a prediction before the fact of saying that, yeah, you could get a really good reduction on this. And that turned out to be true. So little brag and so when I talk about different ways of looking at physics, I'm trying to suggest the same idea. Maybe we could look at the underlying mathematics in a different way and wind up getting at least some different path. Now, simple question. How many bits are in a cubic centimeter of empty space? This was a topic that Richard Feynman once famously addressed in a talk to a huge group of mathematicians at Princeton. And it's also interesting because he essentially mocked his own theory when he was talking about that. He was saying, like according to his theory, according to his entire quantum electrodynamics, a cubic centimeter of empty space is absolutely boiling with energy and computation and bits and all sorts of things going on, just tremendous amount of activity. And after he points this out, he then proceeds to say, yeah, it's probably all wrong. It's probably something more like checkers. And got a laugh for it. So he got a laugh at the expense of his own theory that he got a Nobel Prize for. Why did he do that? Because he knew something wasn't right. I won't say he knew it, but he strongly suspected something wasn't right. But he couldn't figure out what. And he's one of the most honest physicists I've ever seen in things like that. He would always when he couldn't do something, he would always admit it, say, I don't like this. To literally, in the last few papers before his passing, he felt like he had failed on understanding what an electron is. He just couldn't get it to work out right. So following up on Feynman's question, how many bits are in a cubic centimeter of empty space? That's really kind of the center of a lot of what I'm talking about here. Are there none? Maybe there's a few, yes, scattering, a couple here, a couple there. Or you could have, as Feynman talked about from quantum electrodynamics, quantum field theory in general, almost infinitely many transient bits just running around down there, just doing all sorts of stuff. And it makes an interesting, oh, and the other question on that is, if you have bits there, and this is something else I'll get back to, if you do have bits in space, can you store data in space? And can you retrieve data in space, from space? Most of our intuitions are that you cannot do that, and that's an important intuition. So we can say there's a lot of activity going on there, but in terms of persistent bits we can get out, that gets a little trickier, because say, how would I actually do that? And it's not easy to define a definition for doing it. Quantum field theory produces some fascinating results when it's applied to, say, the structure of a proton. Most people have seen this figure at one time or another. If you follow physics at all, you'll see this marvelous little animation done by Derek Lineweber, and it was used in 2004 by Frank Wilczek in his Nobel Prize speech. It shows what happens when you push the calculations down to incredibly short levels inside of a proton or a couple of protons. And what happens is these field, the color force, they call it, as well as the electric force, become just very chaotic. You have this mass of fluctuations that are going on that are just tremendously complicated. So this is not some casual representation Dr. Lineweber did. This is an excellent piece of work in which he did the calculations. He worked this out. And I think people, I remember I did. I thought this was just somebody's casual animation showing quantum fluctuations. Not that at all. This is solid work. So good, such good work that they used it in a Nobel laureate talk. So there's a scale here that's roughly that of protons. So one of the conclusions that people come from this, which Dr. Lineweber states, is that empty space is not empty. It's full of just incredible intensity and density of this kind of material. So very standard and often used in that same sense. Now, there's a funny little twist on this, though. People often talk about this as if this was the same thing as space itself. It is not. This is a simulation of the forces inside of a proton. And if you want to go to space, you have to go 100 billion times smaller. So to say there's a bit of a shrinkage here is an understatement. So you have to go way smaller than what I just showed before you start talking about space-time having frothing oscillations and all that sorts of things. Now, you notice this is someone, it's actually Gerachim, whoever Gerachim is from Wikipedia, did a nice little figure on it, and he shows pretty much exactly what the great Archibald Wheeler came up with, is saying that if you look at space-time very close, you should see a frothy effect, very similar to what we saw in the previous diagram, but at a tremendously smaller scale. And that at this point, you have energy densities that are so intense that you actually form tiny little black holes that appear and disappear. So this was a work he did back in 1955. He actually called them geons. He had a name for them. So if you look it up, it's a different terminology. But Wheeler is one who came up with this, and he gave the analogy about how you can look at these from different sizes. Now, so that's the Wheeler background. Now, to me, though, the more interesting result in more recent times by the great Dr. Gerard de Hooft, a really great man, magnificent thinker, and a very nice person too, by the way. He took this same idea and looked at it in terms of saying, what would happen to the surface of a black hole? And using a certain argument that in which he used a lattice theory, and I'm going to come back to that. He explicitly used a lattice theory. He came up with an estimate of what the number of black hole-like entities would be on the surface. That seems kind of weird if you think about it. You got black holes and black holes. So it's a quirky way of looking at it, but it still captures this idea that at the frothy surface of a black hole, you have these additional quantum effects going on at a very small scale. And at one point in his paper, he just makes a flat out statement, a postulate that one Boolean bit per Planckian surface element, that is kind of an indirect way of saying these little micro black holes, because the Planck energy is the one where you form these little black holes, of which you can see a little, I'm sure, whoa, went to the wrong side. You can see a little example in that one there. So this led to the entire field that is now called quantum, or called holographic universe. From this, other people extrapolated the idea that, well, if you have all these bits on the surface and they have this, essentially not that different from a holographic film, the internal projection of those bits would be a hologram with a finite density, a finite limit, because you have a finite, now very large, but you have a finite number of bits. So this led to the whole idea. If you ever heard of holographic universe, this is exactly where it came from. First, it came from Wheeler's geons, and then you have Gerart and Hooft came up with this elaboration of the idea that these would turn into bits on the surface of the black hole. So fascinating bit of work. Here's another one. This one intrigues me because it's quite different, and never take anything Roger Penrose says too casually. He really can put twists on things and ways of looking at it that are quite unique. And never take what he says casually, even if it sounds pretty wild. I mean, it took decades for me to come around and some of his views on some issues, but on quantum effects at room temperature. And then somebody comes out with experimental results, say, oh yeah, you have quantum effects at room temperature. So you want to take what he says seriously. He came up with this really interesting idea that the resolution to this contradiction that we see between quantum universe and regular universe is gravity. He says that gravity, because it adds a little delta of energy, which he has labeled there as E sub delta, on very small scales, the gravity is so weak, it's not going to have much effect. But as you get bigger, it becomes drastic. So the idea of a quantum superposition of position, for example, which in some ways I would argue is the real quantum superposition. You got to be very careful when you start superposing more complex states. But if position, absolutely, that has been proven experimentally so well, it's just incredible. I mean, gigantic molecules have been shown to go into location superposition. There's no ambiguity about that, because it is just, there's no ambiguity under the usual interpretation. So there are different interpretations where you go off on a different way of doing it. But just by experimental results, two-slit experiments, this is considered an extremely extremely solid result. And I would concur with that very much, because these are very odd effects. They go on all sorts of molecules. Neutral molecules, it doesn't matter. You don't have to be using metals. All you need is two slits and some kind of thing going through it. And all of a sudden you can't define the path that the molecule took. So quantum superposition. Penrose uses gravity, this little energy delta, essentially a little minor curvature in space that adds a little bit of energy to that space, because curved space, you've got energy. And he collapses the wave function with that. Now, and it fits proportionally with a lot of things. Now, one could point out that there's also some issues with this, but it's an interesting theory, and it does add real bits to space. It says that every bit of space, if you have a little bit of curvature there are a few bits. And the bits are permanent bits. They're not just these transient things that were showing up in those previous two diagrams where everything's just frothing around. These are bits that actually persist because you have matter that's sitting there stabilizing that curvature. So I have a little speck of dust, it's 10 to the minus 3 centimeters. It's very small, but in terms of gravitational effects, big enough to make a difference. And we cannot skip Casimir effect. Oh my gosh. Casimir's effect is the electromagnetic version of these drastic fluctuations at small scales. And what Casimir did, with the help of Bohr, Bohr is very much a character involved with this, and people don't realize that. Bohr was the one who suggested the idea to Casimir. Casimir at first forgot to give him credit and later apologized. Said, yeah, Bohr absolutely, gave me the idea and kind of went with it. So Bohr and Casimir. And what are you going to do? Casimir is a solid-state physicist, and one of the most famous theoretical physicists in the world says, "Hey, here's an idea." So Casimir, not too unreasonably, took it as a serious idea, and he proposed this intriguing idea that because the waves block outside electromagnetic waves, you essentially create an incomplete pressure between the plates. Certain modes of vibration just can't be there. This literally happens if you've ever been like boating, and you notice that when you pull your boat next to a dock, the boat tends to pull towards the dock. In fact, you got to be careful. You can get your hand mashed if you're not careful about this. That is the same thing. What is happening there is your boat and the wall and the dock are forming a restricted area in which only a certain limited number of modes of vibration are possible, whereas the ocean has any vibrations at once. So the result is you get a net push inwards to put the two plates together. So this is often called the 0-point energy. Casimir predicted it. A fellow named Steve Lamorix, almost 50 years later, finally was able to demonstrate that this was real. This happens. This is not just an imaginary effect. You can say, well, it probably isn't real, but no, they've done good work and shown it's not easy work, but they have shown that this is a real effect. And this too would be an example of the chaotic aspect. In this case, the chaos really is on the outside of the plates. It's, people think of in terms of negative pressure inside. You need to kind of flip it the other way around, because what's happening is saying that the outside world has chaotic electromagnetic field. They're just going crazy all the time. And then you have a safe area here where they disappear, just like the boat next to the dock. So people talk about 0-point energy, but a better way to think of it is like enormous energy out here, and then a safe space where the energy cannot get into it. And that gives you more accurate. And it shows up in the figure here. If you actually look at the figure, that's what it's trying to show up with this. So Casimir effect, again, chaotic, bit-like energy and bits, close connection with that. So certainly a related concept. Let's take a closer look at this, though. There are some issues. The first one is, let's look at that figure about the excellent calculations done about gluon field fluctuations. These are calculations that help to describe the behavior inside of a proton. So this, I say, this is real. This is work that has experimental consequences. So that is always, a powerful argument in favor of that. And the author of the work made the comment, said, well, this shows that empty space is not empty. Now let's look at that a little more carefully. And the question is really simple. You see it right there. If you could fill, now you can't really do this for all sorts of reasons I could get into, but if you could uniformly fill a room with flux fields, that's a combination of electric and color forces, as you can the ones inside, if you fill a room with that, like you could in a proton, what would happen if you stepped inside that room? And the answer is, of course, instant obliteration of you. It would be much worse than that. It would be, this would be like taking a room-sized chunk of a neutron star and putting it in the middle of your house. And nothing good would come from that. I guarantee you, at least the Earth would be obliterated. I'm not going to do some calculation. Somebody could do a calculation of what would happen. You'd at least do the Earth. You'd probably do in the sun too. So I just consider the whole solar system pretty much obliterated. Now, so the question goes down to this: is that really empty space you're talking about, or is that space filled with one of the most intense energetic fields proven to exist anywhere inside the universe? And I would simply say the latter. Of course, it's the latter, because you have these fluctuations, but these are fluctuations after the existence of unbelievably intense fields. We think of the electric force as powerful at our scale. Think of what it's like inside of a proton. We have oppositely charged protons, a proton distance away from each other, not even including the color force. So you want to be a little careful on that. So I would have the nitpick. It's gluon field fluctuations, which is what is going on, because you have these actual force fields and force particles, versus quantum, which implies empty space. I think we have a terminology issue on that, and you want to be a little bit careful on that. So great result, impressive work. Weinberger did fantastic work on this, and it gives predictive work as far as I know. It shows some of the actual consequences in terms of proton behavior. But you have to be careful about some of the casual statements. Are these really quantum field fluctuations, or are they fluctuations generated by the existing field? Now, quantum gravity, incidentally, there's a good reason why this is not as detailed, and I think I mentioned this before, but there is no self-coherent mathematical theory for predicting this. That's a little detail that gets skipped over sometimes. That when you try to quantize space-time at this level, there's lots of ways you can kind of do it, sort of, but not to the level you can with the gluons. It's not as predictive as that. So this is not a result of real simulation. This is an extrapolation of what Wheeler said about this. Now, focusing more, though, on the idea that space is full of bits that are holographic bits. One of the things that's interesting about Hooft's paper is he starts off very early in saying, using cellular automata. Why did he use cellular automata? 1990s were an amazing time for computer technology. Computer technology was just doing everything, just bits and computation was getting smaller and smaller. It just seemed like there was no limit to how far you could get those. And the physics community started paying attention to this. So the idea of, can we use these ideas, became very much a consideration. You see that in quantum computing. You see that Manin, who actually preceded Feynman by a couple of years, on talking about the possibility of quantum level computing with these devices. So it's not too surprising that cellular automata became a point of fascination, that people wanted to look and say, can we model it better? And they had successes, because quantum field theory, or chromodynamics, the same one that we saw the earlier active animation, those benefited greatly by using a lattice type approach. So what happened is this just really caught on and people started using that. But there's just one problem with this. And it's almost like it's too obvious to say, but I'm going to say it. If you're using a lattice, you're using a single inertial frame and you have abandoned special relativity, because special relativity's vacuum is not attached to a single frame. Never. It just isn't. That was the whole point. Einstein's whole point was you can have 1,000 different observers going 1,000 different speeds, some near the speed of light, some going slow. They all look at the same region of empty space, and they all see exactly the same thing. There's nothing different. To them, that empty space always looks the same. That's the very heart of special relativity, is that there's this amazing inability to see anything different about empty space. Everybody sees the same empty space. Even if they're all looking at the same empty space, they see the same emptiness. If you use cellular autonomy, you lose that. You have to. You created a computing web. The fact that it's smaller doesn't make any difference. It's just like a computing web here on Earth. It's attached to Earth. It's attached to Earth's initial frame. It's no different here. This is not a complicated issue in terms of why that happens. So, and they use this wording. You'll see this in a lot of papers. Seems to conflict with local variance invariance. So that is a kind of a sneaky way of saying, this is so useful, we're just going to assume that special relativity doesn't work. So it's a hypothesis, but it's not stated explicitly. One of Penrose's books, I remember the first time I read all the way to the back of the book, I said, oh, he doesn't believe in special relativity. So you don't get that in the front, but nobody says that out front, because it's too controversial, and people would object if you just say point blank, say, yeah, we think special relativity is going to fail. But the truth is, most of physics since 1980 has assumed that special relativity will fail. And they talk about cutoffs. They talk about conflict with local invariance. There's a whole terminology that goes along with this, but it always says the same thing. You have to assume that if you get too energetic, special relativity is going to fail because it's on a lattice. You can't push your computing lattice beyond a certain point. Again, this is not this is a very computer argument. This is not very complicated. You push the lattice beyond a certain point, it can't do it anymore. It's going to fail, no matter how powerful it is. So that's what's going on with these things. Now, the other point I want to make about Gerard Hooft's paper is this same fascination led to what I would consider way too non-factually based assumptions about technologies that the physicists were not very familiar with, such as what is a storage bit. The idea that a storage bit is the same thing as a data obliterating microscopic black hole, I'm sorry, just from a computing viewpoint, that doesn't follow. The two, and I'm not saying that Hooft doesn't go through an argument, he does. He goes through a lattice-based argument in which he uses the lattice to constrain the dimensions and winds up with bits. But if you start with the lattice, you've already started with bits. You know, if you start with the assumption, you say, I assume that everything is a lattice, and therefore, oh, look, I proved it's a lattice. Of course you proved it's a lattice, because that was your initial assumption. And that is very much what this paper does. By assuming a lattice is the initial assumption, of course you're going to wind up with bits. There is essentially no other outcome. But calling the black holes, the microscopic black holes bits, just kind of arbitrarily, it doesn't follow. Black holes don't behave like bits. Storage bits require structure. They require a lot of engineering, frankly. They require a certain finite amount of mass. That's why you had trouble making bit arrays too small. Back in the 90s, it seemed like bits were just going to get shrink until they were nothing, until they were black holes, I guess. But that's not really what happens with those bits. So problem with the idea that these bits are so common using this approach. Even worse, and this is, I cannot understand why this happens. I really, truly cannot. There was a time that theoretical physics paid every bit of attention they possibly could to every theoretical result they saw, or every experimental result that they saw. That is not what happens anymore. In 2020, a team of about 100 scientists are on the paper. It's an excellent paper, extremely data-based. They looked at the extreme the teravolt gamma rays that are known to exist in the galaxy from 4 different sources. And these are a good test for the whole lattice theory. Because like I said earlier, if you have a lattice here on Earth, if you push it too hard, you try to push too much data through it, it falls apart. And in the terminology of physics, they call that a cutoff. They say we expect a cutoff in which standard physics will fail, is the terminology. And Wheeler's Planck foam was just such a cutoff. He said that after a certain point, special relativity is going to fail. It's going to produce something like this. There are experimental results that say that is wrong. That despite the incredibly tiny scale of this Planck foam, the Halsey 2020 was able to say that in order for teravolt gamma rays to cross the cosmos over this supposed lattice of space-time, they're going to fall apart. They have to, because after a certain point, you lose resolution, and these things are just too intense. So they would fall apart. And what did they see when they looked for that? They saw absolutely nothing. Special relativity, Einstein was right, it held. It doesn't matter how energetic a photon is, it still seems space the same way. So the actual figure, the experimental figure on the right, that one is my figure. I kind of made it from the other one. That's the correct one on the right. It doesn't exist. There is no Planck foam. But people ignore that. They just say, oh, well, it's just another experiment. No, it's not another experimental result. It's 100 physicists using some of the best experimental equipment in the world, getting a very solid result. And you're just going to say, yeah, it doesn't matter. No, you can't do that. You have to take that into account. The simple truth of it is that this postulate by Wheeler failed. by a factor of about 1,800, about 2,000 times. And that's just from the data available. I mean, it's hard not to extrapolate and say that if you go even higher, it's just going to get worse. So that's another reason to be careful about the Planck scale foam, because it's been experimentally disproven. As I talked about, again, I ahead of myself a little bit in this, lattices define a space. They define a network. But the physics model using lattices, since I think it was about, I believe it was back in early, again, I remember reading the articles back in 1980s, somewhere in that range, people started doing it and said, hey, this works pretty well. And it did, it absolutely does. But this gets into this whole cutoff equation, and the one in particular is that where they get the notation, I have no idea. E to the parentheses, not just one, parentheses 1, and then that's the Lorentz invariance limit down there. The cutoff that they expected where special relativity would fail, which most physicists believe it will, even if they don't say it out loud, didn't work. Einstein won. Casimir effect. Oh, I love Casimir effect. There's a problem with the Casimir effect. In 1948, Casimir made a statement. I remember my reaction when I read this paper. I just kind of like threw my hands up in the air and said, you gotta be kidding. You can't seriously say that. He said that the reason why only certain frequencies seem to affect the plates is because the plates are transparent to X-rays. The X-rays just go right through. you can't do that. If you're going to take this seriously, you say the plate, what he did is put in a fudge factor function where the function just says, oh, for reasons we don't quite understand, it just drops off on those higher levels. Now, there's nothing wrong with putting in a fudge factor when you're trying to agree with experimental data. Don't get me wrong in that. His fudge factor function, that's hard to say several times fast, was a genuine function that was expressing something he was observing from what they could see of the data, which was that these things didn't fall off. And yet, within that fall off, you've got this behavior. You've got this behavior in which it would seem to be an absence of oscillations. So this takes you up to 1998, in which Casimir essentially says both at the same time in the same paragraph. He says, clearly we've proven that there is a wave suppression effect that causes the plates to be pushed, but we've also proven indisputably that it's nothing more than a casual fall off of the cohesion forces of the plates if you first broke them apart. And incidentally, on some work I did, I came up with a model of breaking two plates apart. I had no idea that Casimir had used the same argument. So I was very pleased when I saw this. Oh, he does the same argument. But my argument there was just, well, you can break them apart. You don't have to put them together. You have to break them apart. And you're never going to exceed the bonding force, which is exactly what Casimir says with this. So how do you reconcile those two? Because the first thing he gave is absurd. You can't really do that. If you do that, what happens is you incinerate the cosmos. If you seriously believe that every point in space has an almost infinite amount of electric and other force resonances going on all the time, the wave intensity pushing those plates becomes not quite infinite because you have that little black hole limit that Hooft talked about, but it becomes almost infinite. And what really happens is everything in the universe is crushed and incinerated by the vacuum. Period. There's no transparency issue. That you can't reconcile that statement that he made in 1948 with what we've seen in the universe, or with a statement from 1998 that Casimir made. And this to me is one of those interesting things, because if you think about what Casimir said in 1998 and you assume that he did good work, and he did, he established two things at once, but they're paradoxical. What he's really saying is that every time in quantum field theory that you assume infinite energies exist at the lower level, you're wrong. Now, Casimir didn't say it that way, but if you look at the statements, you can't get around it. What it really says is, no, the maximum energy that feeds quantum field theory down to the loops, down to the QED loops and everything, has to fade. And the fading is determined by the maximum cohesion energy of when the masses were first separated. In other words, when if you imagine all of the universe starting as just one ball, and you break it apart, there's an energy that is required to do that breakup. Rather than being infinite, it's quite finite and actually rather small. And that is the energy that drives the field theory. Now, this could be a whole different talk by itself, but I think this is just an intriguing area. Always in quantum field theory, we're trying to cancel the smaller components. So you get away with the infinite energy. So you get these really convoluted renormalization schemes that Feynman came up with a brilliant idea. But at the same time, you're always trying to cancel the infinite energies. Maybe the problem is that you shouldn't be invoking those at all. The energies are those of the matter that you've separated, and you have to put a finite limit on that. So I think Casimir inadvertently gave a very good piece of advice that you have to reconcile these two paradoxical conclusions in order to get a quantum field theory that does not go to infinity. Our maths don't do a good job of that, but he pointed away that there's a possibility that somehow these two have to be reconciled. Not just possible, I would say it's a necessity. If you don't want to incinerate the universe, which is what happens with quantum field theory, if you take Casimir's plate results seriously, and you get rid of the silly X-ray idea, because gamma rays don't have any effect when the gamma rays go through you. No, you just can't do that. So fascinating. That one paragraph by Casimir in 1998, I think, has some really good insights. Quick look at Penrose's collapse interpretation. I said that he shows real bits in space, but if you look carefully, curvature attracts matter, but matter creates curvature. So the problem is in this one is that, yeah, you have bits, but the bits really reside in the particles that are curving the space. Take away those particles, once again, space goes back to zero persistent bits. You can't store anything in it. You can't put anything in it. You can't take anything out of it. You can't store your address in a piece of cubic centimeter of empty space. There's no storage mechanism. Penrose gave an actual storage mechanism, but once again, it relies on matter. The other thing I would comment on Penrose's work here is he sets up this idea of this E delta as being the cause of the collapse. And this is something I've said before in little essays and miniature papers, is why not take that all the way? Every acceleration, not so much the energy, but the acceleration, momentum, changing of the inertial frame. If you're going to say that for that, why not just say any acceleration collapses the wave function? Because that's essentially what the gravitational energy is an acceleration. So I would take that idea that Penrose had, but I would go way, way beyond that and say, let's just flip it all upside down and say that acceleration, every time an acceleration happens, collapses a wave. Now, the reason it's not easy to do that is you have to, it has impacts on your math, to say the least. There's a lot of sunk cost investment in mathematics. For instance, a hydrogen atom would become a continual collapse effect, where the electron is constantly, we think of it as quantum, but actually would be the electron is constantly collapsing because of the attraction of the proton and vice versa. That's why you have hydrogen atoms. They're observing each other. They're sticking together. So I like Penrose's idea, but I would take it much, much farther. And in terms of space storing data, no, it's the matter that's storing data, even in the Penrose interpretation. Chaos versus persistence. What counts as a bit? Now, when people talk about infinite energy and infinite bits and computational processes going on inside of a cubic centimeter of empty space, as Feynman talked about, do any of those bits endure? And the answer is no, because you cannot find a mechanism by which you can store data in that spot and remove the data from the spot. Penrose's idea comes the closest, but again, it's really just an extrapolation of matter again. So if they don't persist, do you really want to call them under the same name? And I would say no. So you could have a different kind of bits. You have persistent bits, persistent information. What is the persistent information, for instance, in a proton? Is it all of that cloud and all of that chaos and all that? No, it's not. The persistent information goes back to the original simple model of the proton, which is 3 quarks of 2 times. Once you nail those pieces of persistent information down, the ones that are attached to actual matter, then everything else arises from that persistent information. And the calculations are real, but you want to make a distinction. Chaotic bits that are arising as a result of processes should not be confused with persistent bits that actually hang in there and stick around. Now we take that hypothesis a little bit further and say in particular fermionic matter, that is the half-spin matter, the matter, the particles that we're made up. Because if you use only the information version, let me get this first. The stationary bits are hard to build, so they're not trivial. And we need to get away from that idea that as in the case of the Hooft paper, that they just kind of appear. No, they don't. The first invention of something that really could be a bit was done a few billion years ago, and it's called DNA and RNA. And those are arguably the first bits. They're quad bits, but they're still bits. And they have exactly that property of persistence of information over time that leads to a much better definition of history and of time. But technologically, these are complicated devices. And as you get smaller, you have flip-flops. Those are very stable. They use a lot of matter. The more you shrink the matter, the more difficult it becomes to make stable information. You can get transitory information, but you can't get stable information. The hydrogen wave function, I would argue, as I mentioned before, the capture of the electron by the proton, vice versa, in which they're constantly accelerating each other, arguably is one of the reasons why a hydrogen atom can store information. The existence of the hydrogen atom in a volume of space absolutely stores information. But it has this peculiar relationship where these things are essentially probing each other. I want to mention one at the bottom there, that the one about electrons. People think of electrons as qubits. They think it was the perfect qubit or the perfect bit, either way you want to think of it. It's classical, like in a spin memory, spin glass memory. You either flip it upside down, you flip it this way, you flip it that way, and you get a bit. The point that people forget in the mathematical models is, where did the magnetic field come from? Because until you accommodate the magnetic field, you don't really have a bit. So you say, well, I'll just put a small magnet around it. Oh, really? How big is your magnet going to be? I would argue that the smallest case you have would again be the hydrogen atom, because you can have the para and the ortho versions of the orbital, of the single orbital, because of just this effect. But until you get that magnet, you don't really have a bit. So instead of saying an electron is a bit, the more correct statement is maybe the smallest bit possible is a hydrogen atom, with the 2 different orientations of the 2 spins of the 2 particles inside of that. So we have to be careful about defining a bit, that we don't get sloppy and make it too small for it to really be a bit. And the other form of information is when you have electromagnetic radiation in particular, but other forms of radiation, neutrinos would also count. But the trouble with these is you need to have receivers in order to give scale, meaning, context, structure to these. So the idea of transient moving bits is a really interesting one and deals with the boson side of the world. But to have bits that are stable and stationary, I think is very important. Until you have stationary bits, it's hard to construct a universe. I'm not saying it's impossible. Maybe you could construct a universe with nothing but bosons just going around, I don't know, gravitationally orbiting each other or something. But it's going to be really tricky. Fermions just are so important for this idea of information stays in place. And when you have information in place, you can see something like me sitting here in one piece, persisting, because I'm made out of fermions. Right? In the fermions, this wouldn't be happening. Same thing for you guys. You wouldn't be out there sitting if you didn't have fermions that were giving you the ability to go straight through time without moving laterally through space. So the idea of stable persistent bits is an important concept and seems deeply tied to fundamental particles. Now, I said I made comments about using fairy dust, about chaotic bits that are disguised as real bits. I'm suggesting that some of our mathematics are part of the issue with why we have so much of this chaotic type of bit structure going on. Again, one example I didn't give in the slides, but I'll give it again. The idea that there's an electron running around inside of a hydrogen orbital only makes sense experimentally when you put enormous energy, like a gamma ray, to knock that electron out of that orbital. In all other conditions, it's a low energy state, simply to say that the electron essentially is the wave function. Now, what we say instead is say it's a superposition of an infinite number of infinitely energetic, infinitely diverse wave functions. Can you see how there might be a little bit of a problem there? Are we taking a generative approach? Are we just launching into the most elaborate, most energetic, most impossible physically, because you can't get a point electron, and saying, simply declaring that to be the reality? So much of our math has certain interesting habits built into it. And until we can get a distinction where we're a little more careful about whether we're just creating chaos bits, or if the chaos bits are really part of the activity, which they can be, but those are usually a much smaller part. A lot of this is chaos bits that I would say is, well, the examples I gave, color force fluctuations, those are real fluctuations. Quantum foam is not experimentally disproven. Casimir is an interesting case because it has some reality to it, but clearly we're not getting the whole picture. So are these chaos bits that we're coming up with these things like the infinite computation in a cubic centimeter of space that Feynman talked about, is that real, or is that a feature of our mathematics? Now, I'll go on a little tangent. Let's find a specific case and examine it a little bit and see if that gives some insight. This is the quantum computing group. You guys should all know block spheres. So this is a standard way to represent a qubit in mathematics. Wonderful properties. I love the way these things work in terms of how you add them together and you essentially move around little pathways on the sphere. So it gives a good idea. You have your stable states at the bottom and the top. Traditionally, the one, I never figured out why the one is at the bottom. To me, it just seems like the zero. Why wouldn't the zero at the bottom? I don't know. That's the way it's been done. So because the zero, you'll see in a second why I think the zero would make more sense at the bottom. But nonetheless, they put the zero at the top. They're arbitrary states. I think everybody could agree. A qubit is completely symmetric between two states. There's no difference between one state and another. It's just an arbitrary bit of labeling. Now, if you look at the deeper structure of that little simple block sphere, this is what you get into. So if this looks a little confusing, that's because you're mapping four-dimensional spheres, which are actually called three spheres. How's that for confusing? Four-dimensional spheres are called three spheres. Three-dimensional spheres are called two spheres. Yeah, you work with it. It can be a cause of considerable confusion. They focus on the surface as opposed to the embedding space. But nonetheless, you have these mappings of a four-dimensional sphere that gives a full complex phase information into a three-dimensional sphere, and that's where the block sphere comes from. So it's called a Hooft vibration, and I don't know if I'm pronouncing it. I don't know. It's Hooft for Hooft. I'm going to assume it's Hooft vibrations. Marvelous work that was done back, I think, in the 1930s, a long time ago. So it's an interesting bit of topology. Now, a simpler way of doing that same thing, which is a figure you're more likely to have seen, is what's called a Riemann sphere. This is a projective space, and I'm going to skip over this quickly, but you can see what's going on here. You've got this ability where you have these little arrows. I point, but if I click my cursor, it puts me on the next slide. But you see, you have a complex plane, just ordinary complex plane, real or imaginary. You know, most everybody's in a community like this have seen this. But you take it and you project it towards that top point. Maybe that's why they call it zero, because that's where everybody's projecting to. So as you project it, you capture where the bit on where the number on the complex plane falls onto the sphere. And when you stretch that out to infinity, you wind up with the bits that are infinitely far away all wind up in the very top point, and the bottom point has only one point. So this gives you another way of understanding that whole messy thing about the Hooft vibration. A little bit easier way. I think at least conceptually you can see what's going on. Yeah, it's projecting into it. But why is it so asymmetric? Anytime you have a mathematical structure that is highly in this case, infinitely, literally asymmetric, to represent a concept that you know is simple and small, you want to wonder, is that really the best way to represent that? Or am I creating math noise? Am I creating chaotic bits in my mathematics that are representing something that doesn't really make any difference? And there are chaos bits. There is fairy dust in this representation. But one of the clearest ways to look at it is look at the density. Now, if you have an integer in complex numbers, they have a fancy name for it. It's called a Gaussian integer, G, square brackets I. It just means that, both the real and imaginary component are both integers. So you just wind up with this grid, a nice little checkerboard grid of the complex plane is all that means. So if you take the checkerboard grid of all the integers in the complex plane and you project them onto the two different sides, you get exactly one for steradian, which is a three-dimensional version of an angle of a sector. So you just get one at the bottom, and you literally get an infinity of them at the top. Now you can't get much more asymmetric than that. That's really pushing the limit. So let's look at this from two different ways. The first one is intuition number one, compression of the complex plane. What if you just took the complex plane and folded it into a block sphere? It feels wrong. You say, oh no, that you can't do that. You're pulling things from infinity, you're stretching them, it's going to get red hot at the top very quickly as you start squeezing everything together on that. So the idea, if you think of the complex plane as an actual physical entity, this just feels wrong. And that's interesting because we like to think of planes as being kind of like physical objects. They're kind of solid like a sheet, they're kind of there. But in this case, our minds rebel a little bit. So intuition number two, this is why the terminology calls these rays, is because this makes more sense. Say, no, I'm not going to do that. I'm not going to compress the complex plane. I'm going to map it. I'm going to map the plane using the same procedure as before. So I just create a copy of the number, and then I project it in, and when it hits the sphere, I just write down that same number. Now, here's the point I want to make. Both of the behaviors, both of these intuitions are based on particle physics, because the sheet concept and the compressive concept is based on fermions and how fermions behave. The projective concept is based on how bosons behave, specifically photons. Now, when you're doing this kind of mathematics that is this abstract, it's good to recognize that you are also taking a lot of physics and inserting them into the concept. When you try to do either of these, you have problems. We'll go back to this one. For instance, in this one, even though you're projecting using classical photons, classical light. Does that exist? No, it does not. Can you do infinite density at the top and record the information? No, you cannot. It assumes infinitely small atomicity and recording devices on the top. The mathematical abstraction may seem like it's a pure form of math, but in fact, you're using and borrowing some very classical physics in order to get it. And one of the most classical features is you've assumed, for instance, infinite light speed. How long does it take you to project from infinity? 0 time, because it's math. Really? Okay, what happens when you apply that to the physical world where that never is true? You're going to get noise. Why? Because the physical world doesn't work that way. We know it doesn't work that way. You project infinite photons into one point. Does the physical world work that way? No, it does not. Photons are quantum. They only become a real path under certain size conditions. Otherwise, they behave more like a wave. So there's some interesting issues that go on with using these ideas and this idea of infinite light speed. That's one that particularly gets me. Mathematics is full of infinite light speed. And people never realize that because it's pure, it's just a standard thing. It's pure math, so I don't have. Yes, well, maybe you do. If you want to use your pure math on the physical world that never, ever does that, you have a potential for causing some disastrous dissonances that don't have anything to do with the physics. They have everything to do with a set of assumptions that you put into it that you can project all this information into one spot, that it doesn't matter if there's an infinite amount of information in an infinitesimal bit of space. You can say that, but can you actually do that in terms of any real system that you're trying to model? So the path I'm suggesting on this in terms of saying where we could maybe make some progress on some areas that have been really stubborn for a long time now is that we make a distinction between persistent bits, like the ones I mentioned for a proton. What is a proton made of? 3 quarks and of 2 types. And once you know those numbers, that's the persistent information that just continues to define a proton. So you flip that upside down and say, really anything beyond that is generative. It's what happens when I put a lot of energy into the proton and I poke it and I knead it and I stick it with a gamma ray. Then I get these more complex behaviors. But to say that the persistent information there is more complex doesn't really match what we see. The chaos bits are this generated part. And here's the bluntest part. Most of these ideas come from 1700s math that was pre-quantum, pre-relativistic, and actually, frankly, incredibly naive. Because 1700s math just assumed that infinite information storage at any point in these hypothetical spaces is just fine. And yet, all information bits that we see that give persistent information are complex structures that require at least a couple fermions, and we don't know any other way to do it. So if you make your mathematics based on ideas that cannot map into the physical universe, you have to be careful. Another one I'll point out is orthogonality. It is extremely common to talk about infinite numbers of dimensions, Hilbert spaces, this, and never consider the idea that there might be a cost for each dimension. What if you flip that around and say that every dimension has a cost? We actually have good physics information for saying that. It's the orthogonality of sine waves. If you want to construct orthogonal systems, you need to get sine waves that are long enough and energetic enough and persistent enough that their frequencies can be distinguished, just like we do on radios. That is actually the definition of orthogonality in physics, and it seems to apply even to our dimensional concepts. You can't just say that orthogonality is free any more than you can say that information is free. You have to make some judgments if you want to model the physical universe. If you're just doing an exercise and what do you want to do, that's a different thing. But for mathematics that fits for physics, we need to be a little more sparse. And this is really the kernel of my suggestion. Sparse bit physics, ones in which we say there's some limited number of bits. Those are the ones that count. Other things generate from those bits. So you wind up with this very thin lattice model of reality, in which you have a very small number of persistent bits that can generate collectively, especially, incredibly complex behaviors, very smooth looking structures, but they're never really that. It's always just an approximation. You know, the classical world wasn't real good on the idea of how small atoms were and whether there was a limit there. But when we kept replicating that, we have to be careful. Sparse bit physics is a way of saying, maybe we ought to look a little closer at what you can do. Now, I'm going to give 3 examples, and then I'll be wrapped up. Quantizing the Bloch sphere. Again, this is ridiculously too complex for a qubit. I'm sorry. I have seen people. I had a conversation with someone. They wanted to apply relativistic curvature physics on some of these structures because they were so complex they could do that. Now, stop and think about it. Are you applying those ideas to what a qubit really is, or just to the model of it? And if your model gets this complex, yeah, you can start doing things like applying general relativity to these, because you've got this enormous fabric representing one stupid bit. And that maybe is not the best way to do that, because one little bit is still just one little bit. Maybe we should be focusing more on saying, how do I get the one little bit working? And then how do I get some models to do it? There are some alternatives for Bloch spheres. One of the ones I like most are approaches that use quaternions. Here's an example. You can map these into quaternions. Quaternions are the next level in the hypercomplex series. You have complex numbers, and you have quaternions are 3-dimensional complex numbers. There's a lovely story about the guy who came up with that. He was so enamored with what he'd done. He actually wrote it onto the bridge, under the Broom Bridge in London. So, but the quaternions are a great little technique, but they only have 4 numbers. And again, you have a much more consolidated version, so you don't have these infinities of shapes going off. I would suggest you could simplify even more, that focus more on, just as an example here, focus more on the key points on the coordinate systems of the quaternion, which are only 4. Now, the 4s are usually given I, J, K, and real numbers as the coordinates. But here, I'm flipping this around. I'm just saying I, J, K are X, Y, Z. And in stark contrast to everybody wants to make time imaginary, I'm making time real on this figure. I'm saying that no, it's the other way around. It's the real axis is the time axis. But you can still take the quaternions and map them into ordinary 3-dimensional space. Now, here's the funny thing about higher dimensional spaces, is you can have 2 rings, both with rotations that are completely orthogonal to each other without interfering with each other. And you can't do that in 3-dimensional space. Our brains have a little trouble wrapping around that. But as you go in higher dimensions, you start rotating it around larger dimensional objects. So if you take a slice of that, what I call intersection slicing, is well, if this 4-dimensional object, if I put it in 3-dimensional space in a certain orientation, what would it look like? And the answer is you get 2 of these. You get one of these, shows that well, you get a representation in which you have the other rotation turns into 2 dots. You only have 2 intersections with regular space, and then you have the other one going around here. Now, just as an example of where you can go with extremely simplified physics assumptions, if you take xy for angular momentum and take zt to be energy, quantum phase, you can produce some very interesting models. One consequence of using this model that I found interesting was I used this model to come up with what's called a dual universe model. And it was actually a very simple exercise, just playing around with these small number of bits. Well, then I found out that Boyle and Turok had done their own version of that, and I got into a conversation with Latham Boyle. And I think we were both a little confused. He thought I had gone through some extremely complicated mathematical analysis, some of what they did to come up with that, with continuity functions and that. And all I had done was play with quaternions. And yet I was saying some extremely similar things to what they were saying in that. So without saying that this is a good theory, that it's an interesting way to look at things where you get very sparse bits. If you look at the structure here, the fact that you have a loop that is jittering between the z-axis and the t-axis, and what we usually think of the axis of spin, is an interesting statement about quantum uncertainty, because you're saying that you've got something hidden that you can't quite see, and it's jittering back and forth between our usual definitions of time. So these paths give some interesting ways to think of problems in new ways. Here's another one. This is one I did a full paper on a little while back. You can model all the particles on first generation of fermions as a tesseract. And not only does it work, it works really well. You wind up with 2 sets. You have the up fermions, which go up, literally in terms of charge, but also in terms of some of the properties they have, the weak isospin. And yes, I'm getting some deep in some terminology. These are T3 weak isospin tesseract bridge vectors. So you actually represent them as the 2 opposite sides of a tesseract. Because this is a tesseract. I mean, it looks like 2 cubes lying between them. That's a full tesseract I've drawn there. And the vectors that bridge them are the weak force. So you wind up with the weak force not just being important, but actually more fundamental, that it's actually part of what defines what these things are. Go in the opposite direction, you get the down fermions. You get a different set of these things. This includes both fermions and antifermions. But again, a simple structure that is surprisingly robust. I did not come up with this cube originally. Glasgow was the one who came up with that cube, which again surprised me greatly. I thought I'd come up with it, but then I did a literature search and I found out, nope, this has been represented back in 1979. Now, another example of collapsing, the idea that the top one here this is called a pion. The top one has a very complicated set of interactions of gluons. So the collapse idea, the idea that you need to focus on what are the persistent bits, collapses it down 2 levels. First, you go down to using the totem terminology of, oh gosh, I forgot his name, physicist who came up with some ideas for organizing quarks. First, you collapse it down to like 3 different particles, but then you just find one you say that no, basically it's just one interaction going on, and that all the higher, more complex ones are the ones you get when you poke it, when you generate it, when you add external noise to that thing. So again, it's a generative approach as opposed to a superposition approach. And it's not saying superposition is the wrong way to do it. The trouble with superposition, because you have to, because the superposition works, but it says that you're going to get less noise if you focus a little more on where it's coming from. So, summary. I would say physics is actually, people sometimes say physics is so complex that we'll never understand it for 1,000 years. I've heard good physicists say that. I don't buy that. If that was true, how could Einstein have ever done what he did? How could how could Maxwell have ever done what he did? They didn't have all this enormous detail, and yet they were able to come out with very good theories. So I don't buy that. De Broglie, he came up with his famous wave particle duality literally by poking around on an algebraic equation with 3 variables and just looking at it, staring at it for a long time. And eventually said, oh, well, this kind of seems to mean this. Dirac, when he did his work, same thing. He just kept looking at a simple equation saying, there'll be some way to do this. And came out with that. So I don't buy the idea that the universe is infinitely complex. I think that's the chaos bits talking to us. Complexity of current theory, I think we really need to examine our understanding of mathematics as fundamental. When the math is based heavily on physics, which it is, planes, right angles, distances, all these things are taken from physics, ray projections. These are mixes of bosonic and fermionic physics that we have not acknowledged in our mathematics. Our mathematics need to get more quantum aware, and by that I don't mean just keep modeling quantum mechanics using the same exact models that have these problems. We need to think a little bit about whether we need a mathematics that is itself more uncertain. So I would say that the goal to make progress in physics is create elegant but extremely sparse models. I gave some kind of partial examples of just what I mean by that with those 3 early ones, and saying that focus on this idea of persistent bits. Which are the ones that are hanging around there stubbornly and they don't want to give up? Why do those create these other more complex structures? Mixed in with this is the idea that we really need to understand space and time better. Abandoning special relativity because lattices are good, but they're single inertial frame, that doesn't cut it. You can't just abandon special relativity. You have to acknowledge there's something very weird about how space works, and we're not quite getting that. And the talk I'll be giving next month, a month from now on the 15th, I'll examine that a little bit closer. As you see, I'm very much a fan of Einstein, but he also missed a parameter. And I can show you extremely specifically which parameter he missed, why he missed it, and why it has consequences. And the consequences are fascinating because what looks like smooth spacetime turns fractal. So you get spacetime that's broken up by the material objects inside of that. I don't know what the full implications of that will be, but I think there's a missing parameter, and we need to look at it. And with that, I am done.
Thank you for the great talk. And if you have any questions, please feel free to ask.
Yes, thanks very much, Terry. It's quite interesting and a bit complicated for some of us. I just wondered at the beginning of your presentation, you talk about bits and information, and you didn't quite come out with a definition of actually what information is. So I wonder if if by information you mean bits, and then if you mean bits, you mean spins effectively, isn't it? Can you comment on that, please?
When I gave the definition of information, I am specifically talking about bits and actual physical constructs of bits, like the examples I gave earlier. For the simplest bit I can think of would be an electron in a magnetic field, the magnetic field presumably created by another particle, such as a proton. I would say that's an example of a two-state device that gives bits that persist over time. So I am using a specific definition of bits in which I'm attaching them to material objects and saying that only these versions of bits have this property of persistence. Persistence just means they're historical, that you can actually create a history. Of course, without a history, you can't create a timeline. So there's an intimate relationship with how we define time. Those are a remarkable and strange set of properties. And I think because we're swimming in the fishbowl, we have it all the time. We have persistence, we exist, we stay here, we're stable. We don't realize just how remarkable, absolutely remarkable that is. And those are the definition of bits. So yes, I'm trying to make bits into actual material objects in which and that's why I went through the whole space argument, saying that can you have bits in space that allow you to actually store data? And I think most people say the answer is no, that even if you assume space is very, very complex, you can't use it as a storage device. You can send a wave through it, but then you're cheating because you just added energy. As soon as you add energy, the energy carries the information, not the space. So empty space is empty. And one of the reasons why special relativity works is because the fact that it's empty means everybody sees the same thing, nothing. And that's very heretical in terms of quantum field theory interpretation. And yet, Casimir was the one who said it. You can't really have quantum field theory and those other properties at the same time.
How do you reconcile with the string theories as you go to smaller and smaller particles, or almost non-existent particles?
Good question. And I avoided string theory because I didn't want to get into that whole thing. The figure where I showed you the experimental consequences of the 2020 gamma ray observations, experimentally eliminate not only geons and Wheeler's quantum froth, but they also completely eliminate all versions of string theory. So if you want to go by the experimental result, you can't have string theory because it doesn't match observed reality. The scale of the strings are far too large. They're like elephants trying to thread a needle in terms of that. They're the same scale as the Planck constants that Hooft talked about. So now that's not a popular statement because everybody just loves string theory and the vibrations. There's a fascinating history on where string theory came from, and it's just one of the incredible sequence. But the real string theory is hadronic string theory. That's where that's the original, that was the name of it, was string theory, was how the quarks are bound together by the color force. The color force are the strings, and they behave literally like strings. They are the universe's smallest strings. But then it got borrowed and scaled down 20 orders of magnitude to create superstring theory, which has never been proven. Hadronic string theory is incredibly well proven. It's just quark orbitals. So they scaled it down, made a hypothesis, and abandoned all particles. So not surprisingly, it does match. So none of this is compatible with string theory in any fashion because string theory, again, has been experimentally disproven, even if it's not widely acknowledged. If you've got an entire department based on string theory, what are you going to do? You say, oh yeah, there's an experiment that just told us our whole department doesn't make any sense. That's a tough one. I acknowledge this is a tough one, but you can't do it.
Yeah, but mathematically, well, I don't want to dwell on this, but string theory to some extent has shown some resilience for mathematically. Experimentally, you might be right that they haven't proven yet the theory. But going back to this question of information, so if suppose that the string theory was correct, so then as you go to the string level, so you would mean that there is no information, that you cannot preserve information.
Say the question again.
I was saying that let's imagine that the string theory is correct, and I'm saying as you go down to the string level, to the lowest levels of vibrations of this energy, when you reach that level, it means that you wouldn't be able to have information based on your definition that you require fermions.
Well, actually, if you assume string theory is correct, you have infinite information, because each string it is a storage device. So and that's where that's contrast from what I'm saying about the sparse one, is a string theory. Think about what a string is. First of all, it has infinitesimal small diameter. It has finite length, which often they'll say, well, that's why it's not infinitely energetic. But no, the infinitesimal diameter gives it infinite energy, infinite precision, infinite energy, infinite information content. So every string captures any amount of information you might want. So if you assume string theory is right, the information is absolutely saturated with real causal information. But it also is what causes a lot of the problems with that. And again, I can't help but go back to it. It says that the idea of these strings, even in every version I've seen, is incompatible with experimental results. They have been everything, quantum loop gravity, the froth, the strings, all of those contradict the Lorentzian invariance that is seen at that scale, because we don't see any structure down there. By a factor of 2,000 is not a small margin. So strings have all the properties of classical matter. They have inertia. They have ability to revolve. They have chemical. They have what we would call chemical cohesion, because creating a string is very difficult in the physical world. So all these properties are just given to them, just attributed to them. They have cohesion. They have length. They have inertia. So once you have all those things, you have to get regular physics popping out of them at different levels, because there's no other choice. You already have most of classical physics in them. So, but I would leave it at that.
That's fine. Thank you. Thank you for your answers. Bye.
Terry, I really like the way your talk and the way you have analogies. It fits my thinking very well, and I appreciate that. My question is, based on this information energy paradigm that you have, what do you see the possible options for a quantum random access memory, QRAM system? Is it possible to have that? Or is this something you see to possibly being developed in a certain medium? What are your views on that?
For quantum information, one of the things that what I'm suggesting is that the actual storage information, again, is very limited, and literally goes on just the standard estimates that you get from mass energy allows you to have so much information. In terms of quantum computing, I think there's some really interesting issues here, because this goes back, when you take the sparse bit approach, many of the most interesting behaviors coming out of, for instance, molecular quantum computing, which is a real thing. Biochemical molecules seem to be able to compute results in ways that we don't quite get. They do it extremely efficiency very often, and at extremely low cost, and they're not accidental. They're part of the design features. The understanding how that works, I think, will depend in part on getting rid of some of the noise parts. And so I don't think we can have a big increase in storage, but I think quantum computation could get very interesting if we take more of a sparse approach. And then we actually would find out quantum computation is not as hard as we thought it was for certain situations, because the universe does it all the time. I mean, none of us would be alive and sitting here if our cells weren't doing trillions, quadrillions of quantum-ish calculations in terms of how to configure themselves all the time. And we don't have a good grasp on that yet. This was talked about. Manning talked about that, immediately switched to computers, which is hilarious because he nailed it and said, all these molecules are so efficient. Let's use computers instead. It's a hilarious juxtaposition of paragraphs. But we're missing something there, and I think it's a good opportunity.
Thank you.
Notice there's a comment from a participant. The comment is Casimir in hydro analog requires energy source. The big question is what is this source in physics? Electron clock creates pilot wave may be sufficient.
Ooh, yeah, and when I have a slide about the Casimir incineration problem, that's actually what I was saying, that if you take the same quantum forces that Feynman talked about, saying like, this doesn't seem right. There's so much energy in this 1 cubic centimeter of space. If you take that, that is your energy source. You're saying that this empty space has almost infinite energies. That's where you get all these conversations about 0-point energy is coming from just that point, or just that issue, is that you have to compress these, and you're assuming that there's infinite frothing of the waves in all of the empty space around you. But it's paradoxical because that level of intensity has impacts, and Casimir kind of skipped over it casually. What Casimir, I think, is getting at with his statement about cohesion is more interesting, is that there is a source of oscillations, there is a source of energy, there is a source of these, but it comes from the matter itself. It's a long-range, and this Casimir essentially says that exactly. It says it's a long-range relationship between the clumps of matter. Feynman talks about this. He gives a precise calculation about the intensity of these things. So I think we have to recognize the reality of these fluctuations, but realize that also they're attached to matter. So not sure how good of an answer is, but that's the best I can get.
Yes, sure. So personally, I agree that I'm just organizing a conference about Täterbewegung, and some people are saying that this clock is propelled by some noise in the vacuum, but I don't even think it makes sense. So I also search for a clock of the particle. So we need that the clock itself also neutrino oscillations. Also, a resting neutrino has oscillations. So we need this proportion for this mechanism of this oscillation. So the question is, what is it? So if you have something interesting, I have a conference 27 March. I'm organizing. If I will put information here if somebody's interested.
Okay. Gerart, could you maybe repeat your main question or observation?
So personally, I have a clock mechanism for electron and for neutrino oscillation. So okay, I can put my recent preprint for this 25 was 01.
Maybe put a reference or a link.
Okay, so okay, I put okay. I have so here is my clock mechanism. Okay, so this is my recent preprint on the chart. So the question is how to make the resting clock already, the resting particle already has a clock. So there is mechanism which comes from my complete model. So this mechanism says, so this is very simple article for the phi to form the kink, this 1 + 1 dimensional soliton. So we need to add to make it a time crystal that in the lowest energy state it already has a tendency for oscillations. So this mechanism using the curvature squared energy terms, which literally for non-negative temporal derivatives of the space brings tendency for non-negative spatial derivatives. So I have some mechanisms, and if somebody's interested, there will be a mini conference in 1.5 months. So okay, I'm just searching for the link. I put in a moment.
That sounds interesting. Of course, I would agree that every particle has a clock because of the oscillation issue. Energy, mass is a clock. You can't separate. This
Sure,
is
but what properties this clock? That's the question.
what's that?
What is the mechanism for the propulsion of the clock?
I,
So
I
that,
think
that,
that's,
that's
I think that's a really interesting question. I think that's where we
yes. So.
understand that better.
So if somebody is interested, so we have a conference. I will put the yes in a second. Okay, so here is the I put the link for the conference we have. So there are a few persons. So personally, I have the mechanism in the preprint above, and we already discuss it. I'm not certain if all the particles have it, but for definitely for electron it's confirmed experimentally, and for three neutrinos. But besides, we don't know what's happening with other particles, and so it should be 2,000 times faster for proton, and so we don't know, but it's too difficult to measure it. So if somebody's interested, I think there is like one or two slots in this mini conference. So.
I'll take a look.
Especially if having some mechanisms.
I can't see the conversation right now, so I can't, but I'll take a look.
Thanks.
Any other questions? I am fine with wrapping it up.
Yes, there is a question. You were talking about very high level concepts, and I'm not trying to level up with the level of sophistication here, but I have several naive questions. First of all, when you mention sparse, what does it do to the density matrix? The other thing is, when Einstein was talking about warped space, can I understand it in terms of sparsity or quaternions?
Good questions. Yeah, as I mentioned before, with the sparse approach, if some of the math would have to be, how do I put it? One way I've expressed it a couple of times is that if you flip the axioms upside down and say your first and most critical principle is conservation, period. Conservation, any kind of probability flow, the idea that the first principle is conservation, then you get the symmetries come from that, which is literally the inverse of Noether's. I don't know how to pronounce her name. I've always pronounced it wrong. Noether's theory.
Noether's, Noether.
How you pronounce it though?
Lady. As you wish, with my accent, pronunciation is very secondary as long as I communicate.
Oh, but it would, you would literally start with finite conservation of mass energy and then properties that come out from that. And your second question was, I'm sorry, again, second question?
About warped space, associating it with
the best
singularities, sparsity, quaternions, and
the best argument for space having existence, I think one of the reasons why people think there is a space fabric is general relativity has shown us that curved space-time is a very good way to model what happens, an incredibly predictive way to do it. So to use a sparse bit model, what you have to do, and this is not just in general relativity, it's on a whole bunch of things. You have to go to a model where particles interact directly with each other in ways that are not standard, that they're more like quantum entanglements. So you can get in some of the quantum entanglements theories of spacetime would be one way to express it, but I think entanglement's kind of a clumsy way to get at those issues. But clearly the particles can interact in ways that don't follow the usual definitions of space and time. And curved space would then be a product of those relationships between that. And I'll get into this next month, but this idea that space-time has a fractal structure because you have you have a serious conflict between two definitions of time, which is time that has progressed, that you've actually seen and observed, versus time as defined by physics. Those two don't match after you accelerate a system. They actually come into conflict with each other. And that seems to have some kind of relevance to the overall understanding of space-time structure and would have some kind of impact on general relativity. Because if you can't reconcile two different fundamental definitions of time, you're going to have some issues, and they seem to have some correlations. But we don't understand well how particles fully interact with each other. We see the specific interpretations of them as waves or as particles, but something much more entangled and much less localized seems to be going on underneath that. And I think that it's just a fascinating area, but I don't think it's an easily resolvable.
Yeah, well, time is known as problematic, but if I can draw some tool from the surprise bending of light, and light is very basic and very essential in all this discussion. If light can go around the corner, which was a surprise talk to me, or can exceed the speed of light, the famous c, maybe we can do some paradigm shift of our understanding of time. And as they do as a trick in differential equations, you do stretch coordinates, slow time, fast time.
Yeah.
Maybe we can allow different intervals of time to behave differently than what we think time is in a linear way.
Yeah. Were you aware that Einstein in, I think it was 1911, he gave a paper in which he specifically added an additional condition who said that since we cannot tell that light goes at different speeds in opposite directions, this was a big issue back in Lorentzian time. It seems strange to us now. But in the Lorentz formulation, light could go at different speeds in opposite directions. And Einstein said, well, I've proven that you cannot do that. Therefore, I will add the additional constraint that light is universal in both directions, which is kind of funny because he just spent in that same lecture a lot of time dismissing two arbitrary constraints. And then he literally, and even calls it an arbitrary constraint that he added. The reason that's important is because once you eliminate the added constraint that Einstein did, you have a better resolution of frame-to-frame time relationships, which gets back also into this issue about disparities in time definition. So you have the best definition of time if you assume that everything that has accelerated from some state essentially experiences time asymmetrically, that our speed of light asymmetrically, that the speed of light goes faster in one direction and slower in the other for them, but they can't see it. So it just this lovely combination of invisibilities that you see, and yet you can't just ignore them. But as I've told friends sometimes, that if you have the speed of light going 1 billion times faster forward and 1 billionth of a time of the speed backwards, there is no experiment I can do in the universe to disprove that. Derek Muller and Veritasium once gave a nice video on this issue. And you can't. People have tried, but it turns out you can't do it. But the reason you can't do it is because it's fundamental to special relativity. You can't have special relativity without that property. So I would agree. There's more to this issue of speed of light. You mentioned speed of light, the geodesic. Well, yeah, but a photon's not a particle. A photon is a wave. So when we see a photon coming from a gravitational lens 10 million light years across, it didn't cross it as a particle, it crossed it as a wave. So we have to be a little careful even about the classicality. There's a quantum aspect even to that definition of space-time curvature.
And wave has to cater or observe the curvature, namely changing its own properties.
Yeah, I think I heard that.
Can I entertain you with something which is quite imaginary? And this is, why don't we think about Doppler effect of sound waves for light?
Oh, sure. Relativistic Doppler. If you look at my website, I have a whole little thing in which I have someone pretending to be Einstein and talking about looking at the results if they were actually traveling at the speed of light. The only way you can actually reconcile some of the time dilation to this is use the relativistic Doppler effect. That is actually a better and more fundamental description than Lorentzian contraction. And it's well studied for for different kinds of cosmic jets. That's where it first came up. But you really do need to do that. And if you don't use relativistic Doppler, I was not aware of that area. I had derived an equation and I was looking around on relativistic Doppler. And here's the same equation. So it's just the same one pops up. It has to. And Lorentz contraction turns out to be an average of the Doppler and its inverse. So you can make a strong argument. I think actually a simple argument that Lorentz factor is a composite factor. It's not the final word.
Wonderful. You inspire a first for me, but it's well known for you. Great.
Well, it's a great relativist. That's a great question. I love the relativistic aspect.
Yeah, thank you so much.
Thank you.
Is it okay for me to ask another question?
Oh,
In the beginning of your presentation, you talk about this AI, the Chinese AI,
yes,
DeepSeek, and then you spoke about the holographics.
Yeah.
So I wonder, I'm not familiar with this, with the ideas of holographic being used as a storage. So I wonder if this holographic that you mentioned is just a mathematical tool or the physical storage.
There's two answers to that. The holographic storage that I proposed, which is, by the way, is my talk last month. You can find references to the paper, to the slides, to these slides, and to the video that I gave on November 2nd. Is that right? So back on November 2nd, if you look at Apobistia notes, Google Apobistia notes, you'll see a trio of lectures that I gave about the holographic interpretation. The first answer is holographic storage is absolutely a real technology that people are using, but only experimentally because it's never gone out into the theory. You use light, and essentially you make a dynamic hologram, one that you can change and alter. And so that's a real technology. And the other part was the analysis I did on looking at the details of how the whole transformer model works, is that my conclusion was that they accidentally used holographic storage, that they came up with these quasi-dimensions, which they do talk about, and the quasi-dimensions are actually data-defined. There's terms for these when you do it explicitly. And that they were developing them almost accidentally, incidentally, which is a very costly way to do it, essentially by slow evolution of dispersing trying it and trying again until finally you converge in a set of quasi-orthogonal dimensions, which are like codes, and they use this in radio and cellular transmission. This is not a new technology. But the way Hopfield did it is he kind of did it accidentally, and I don't think he had any idea what he really had done. He attributed it to being like biomolecules, which I think was a huge mistake because it's not. It's a very different phenomenon. He was just talking about fault tolerance. But he came up with an incredibly clever holographic algorithm, is my assertion. In fact, that's something I want to work on, is give an actual proof that it's that even his original Hopfield network is holographic. And I think that would be a fairly straightforward proof. So the assertion I made about the LLMs is just that they're all holographic storage devices. And one of the reasons why they're so powerful for answering questions is a holographic interpretation allows you to change perspectives very easily, which is literally what you do with the LLM. So it's kind of like conversational version of a hologram. You know, you look at it from a slightly different angle, you see a slightly different conversation. And I just think that's a really good model for understanding some of this. And in the case of DeepSeek, they seem to have confirmed at least one aspect of that when they went out and pre-constructed the quasi-dimensional structure. They said, oh, it is quasi-dimensional, so let's go out and define the quasi-dimensions. And it was a very clever, they did a straightforward, clever way to do it, which was good data sampling, so they didn't do anything really convoluted. Convoluted, that's almost a pun in that context. So they didn't do anything very complicated, but it worked. It worked really well. So enough so that it just embarrassed a whole lot of people. And it goes farther than that, because using real numbers as bits in a hologram is just not a good way to do it. You're complicating the access to them by making them into matrix multiplications. What you really need is probably a more direct bit level holographic access memory. And I suspect some of these systems could be shrunk down to incredibly smaller size and less power requirements, especially if you use optics. Optics are so good at Fourier transforms. So, and matrix multipliers are not. That is the most expensive way to do a Fourier transform. Well, it's not the most expensive, but it's sure not the best way, especially if you don't realize that what you're really doing is a Fourier transform. So I think there's still a lot of potential in that. I want to put in a qualifier that I am not an LLM advocate. I'm actually very unhappy with how they've been presented as being intelligent. They are databases. And so I would also adamant on that viewing them as holographic databases or as just some kind of a database. You can also say they're just probability word pair databases, because every bit of data gets converted into a probability word pair. And then you wonder why you get random results. Well, if your basic storage mechanism is not a bit, but instead is a probabilistic, as in it can change each time you query it, word pair, well, yeah, you're going to have trouble no matter what you do on getting to have completely solid answers, because you essentially corrupted your data at the most basic unit of storage. So I have a lot of problems. There's a lot of strange things going on with the whole LM where they sound very good, but because of that fundamental decision to use probability word pairs, which are, I mean, look below the transforms. Every bit of data is a probability word pair. Marco Polo pairs, I like to call them sometimes. Marco Polo, you know, what's your chance? If I say Marco, what's the odds are you going to say Polo? So that's essentially how it's stored in all of these databases. And these should not be presented as being sentient. They cannot do analysis. If you ask them, give me a summary, they'll give you a summary with some inaccuracies. If you ask them to give me a detailed analysis of why this is wrong, they can't do that unless they can grab one that's already there, and even that they'll get a little bit off. So I think real AI technologies are coming someday, but this path is not the right one.
Thank you.
Any other questions?
Yes, I noticed a question from the chat from Doug. Do you think there's a superluminal instantly transfer of signal as there's experimental violation Bell inequality, even that under the constraints of special relativity?
And again, this is one that if you poke around in my website, I don't even believe that there's such a thing as non-locality. And the reason is you never get non-locality until you get a speed of light signal to the other location. So, the first one who pointed this out, physicists whose name I always have trouble come to me in a minute, but a really good physicist mentioned this, one of the final papers he ever did, that when you change, if you collapse a bit that's entangled with something at another site, nothing changes at that other site. There is absolutely no change. The only time you get the correlation is after, at the speed of light, you reach that distant site, and then you get a correlation. And I just thought it was the first time I read that, I said the most marvelous statement of how non-locality really works is that it's not really non-local, that you have a finite spread of this wave that goes at the speed of light, And until it arrives, nothing happens, nothing changes, nothing's impacted whatsoever. Now, if you want my deeper and even more speculative, well, no, it's not speculative yet. If you want my interpretation of what's really going on there, is we have too rigid of a concept of what space and time are. That what's actually happening is we are constructing space-time definitions of what we think happened after the fact, whereas the actual physics is something a little bit weirder, and we don't have a good handle on that yet. And that's why we get, in certain cases, we cannot create a coherent space-time construction of what happened, because it's just not there. We're accessing physics that don't work quite that way. But in terms of sending a signal faster speed of light, entanglement doesn't do that. It changes your interpretation after the fact, but it never does it faster than the speed of light. So I have a little article somewhere about non-locality as a bogus concept, that we need to stop thinking that way because we're assuming an overly rigid definition of space-time. Anyone else?
Yes. I was wondering, at some point you mentioned DNA and RNA.
Yes.
And I apologize, I heard it outside in different conditions. We have a lot of snow here today. And my wonder is if the concepts and paradoxes and paradigm changes and so on, shifts, maybe do you see a usage of those to biology and medicine?
The bit storage at the DNA and RNA level?
Yeah, biology, cell-cell interaction or signaling is exchange of info.
Yes. I think cells have this worked out to a level that we are still just poking at. And the reason I say that is this: they figured out that the best systems have a combination of digital, highly historical, extremely classical information, which is DNA. And apparently they may have started with RNA, but they got this DNA thing down just right. And yet they also use the Hopfield mechanisms, which is where he should have gotten his Nobel Prize, and rather than the other one for his 1974 papers, I think that's right, 1974 papers, on how molecules are doing some kind of quantum computation and figuring this out. Cells use both. They don't have this rigid line that we keep trying to force everything into. Everything's all digital. It's got to be a giant computer. No, it's not. But they use the tools that seem to fit. And I think we have a lot to learn from cells. And I think there's a huge benefit from understanding that aspect of biology better from a more physics level. How are they combining digital and quantum to optimize the properties of both? And I think cells are very good at that. Why they survive so well.
Yeah, I've been causing some noise and surprise amongst biologists by telling them that bacteria, what's the bacteria? Maybe we can build a computer based on bacteria.
I would not be surprised. I think that's an intriguing assertion. I really do. That is because you're getting at that idea that quantum computing, molecular room temperature quantum computing goes on all the time in a bacterium. So why not? This is where I wish Manin had gone a different route. Manin just immediately, so fascinated by computers, he flipped instantly just after talking about the computation, quantum computation in molecules and how energy efficient they were. He switched to a model that essentially encumbered the concept of a qubit with giant computers that are hyper classical. So I can understand why it happened. I just wish he had gone another route. But I think that's an intriguing idea.
Yeah, you mentioned the name Menon?
Manin, M-A-N-I-N. Yuri Manin.
Yeah.
I should look him up. He's got, again, on my website, I've got some, sarchive.com, I've got some good quotes from him. Just if you look at my website, I think they're down in the bottom. It's just a list. I haven't tried to order anything, but I've got some nice quotes from Manin. That might be a
Mathematician?
mathematician. Yeah, Yuri Manin.
Okay, I came across the name.
Same one. But he did some marvelous writing about quantum computation early on. I think it was actually some lectures from University of Moscow.
Wow.
Radio.
Okay, fantastic. Thank you again.
Thank you. Anyone else? Ellen, are we a wrap?
So if there's no question, please check out our next event on March 15 with Terry again. I just post a link on the chat, or you can search for Washington, D.C. Quantum Computing Meetup, and you'll find the link to sign up for the event. And thank you for all coming.
Thanks,
See you
everybody.
next month.
Thank you, everyone.